Hey everyone, Mrs. Fallon here. We are on page 197 of your student journals, Unit 7, Lesson 7.1. So what we're going to talk about in this little section here is just some vocab and then kind of understanding some of the theorems and properties that are kind of explained a little bit in here. So first and foremost, let's talk some vocab. So first is a diagonal. You might already think you know what a diagonal is, but the geometric term for it, or the wording, is it's a segment that connects two non-consecutive vertices. So consecutive means that they're in a row, right? Like 3 and 4 consecutive numbers because they follow each other. Non-consecutive vertices imply that there are two vertices that are not next to each other. So let's, for example, I'm just going to kind of draw, I don't know, a pentagon or something here. I'm just going to pick some 5 points, and I'm going to connect my dots. Okay. So I'm going to draw this polygon. 1, 2, 3, 4, 5. So it's a pentagon. So a diagonal would be, if this is a vertex, this would be a consecutive vertex, this would be a consecutive vertex. So the diagonal would be like here, could be here. So that from this one vertex, I have 2 diagonals. And then let's say from this vertex, again, can't count the sides as diagonals, those are consecutive, but I would go to here, whoops. Let's try that again. Let's go to there. I could go to here, right? And then, of course, not back to the other one. So I have 2 diagonals from here, 2 diagonals from this vertex. From this vertex, I already have the 1 diagonal drawn in, but I need to add this one. So I have 1 additional diagonal from here. We'll call this D. From this diagonal, it looks like there are no additional diagonals, and same thing from here. So in this particular pentagon, I have 5 different diagonals. And so that's kind of that's kind of the method I use to kind of count or to figure out how many diagonals I have in a polygon, is just kind of use, start at one vertex and just kind of draw in the diagonals and then count from there. All right, equilateral polygon. An equilateral polygon means all sides are congruent. So you've done this with equilateral triangle, right? All sides were congruent, but an equilateral polygon is kind of the same deal. It just means that obviously not specifically just a triangle, but it could be a square, it could be a hexagon or an octagon, something like that. Equal angular is kind of the same deal, except now we're talking about angles. All angles are congruent. So in an equal angular polygon, again, kind of talking about any type of polygon, so triangle, quadrilateral, any kind of like pentagon, hexagon, octagon, nonagon, heptagon, trying to think of all the other ones we know, decagon, dodecagon, all those kinds of ones. We would say that if it has all the same angles on the inside, we call that an equal angular polygon. And when it's both, a regular polygon is both equal angular and equilateral, or yes, equal angular and equilateral. So a regular polygon, and there's a little bit here, we have to talk about being a convex polygon. So if you do remember the whole concave versus convex, so convex is kind of like your traditional looking polygon, right? Whereas a concave has, for lack of a better term, vertices that kind of, sides that kind of cave in. So this is called a concave polygon, whereas this is a convex. So when we talk about regular polygons, we're talking about convex polygons. And then we're going to say they're equal angular and equal lateral. All right, so again, kind of thinking back about like an equilateral triangle is also equal angular. That holds true if it's a regular polygon. A square is equal angular and equilateral. If you have a regular hexagon, again, it means all the angles are the same, all the sides are the same. All right, so let's talk a couple different theorems. So theorem 7.1 says polygon interior angles theorem. The sum of the measures of an interior angle of a convex, so again, we're just talking about these types of polygons, convex, not concave. Just let me write that down. All right, so the sum of the measures of the interior angles of a convex N-Gon, and that just means any polygon, is n minus 2 times 180, where n represents the number of sides. So, for example, if we have a figure, right? So if I have a 6-sided or a hexagon figure, n equals 6, right? So the sum of the measures of the interior angles would be 6 minus 2, so 4, times 180. And so that would be the sum of all the angles inside. So think about a triangle, right? We already know that a triangle has 180 degrees, right? All 3 angles of a triangle add up to 180 degrees. That's because there are 3 angles on the inside, right? Well, 3 minus 2 is 1, and 1 times 180 is 180. And so that polygon, triangle is a polygon, that polygon holds true for that specific example as well. Let me kind of switch gears here, and I know that I gave you guys in class, and I also posted on Canvas, but I printed off some like extra examples, and I just thought it might be handy to have these examples, or you can always just draw them down as well. All right, so on this one, this is an example of this theorem right here, the 7.1. We're talking about the interior angles of a polygon, so a convex polygon. What I would do here is I know that this is 1, 2, 3, 4, 5, 6-sided figure, right? So this is a hexagon. So if I want the sum of the interior angles, I know that it has to be using the formula n minus 2. I'm going to substitute in, 6 for the number of sides, so 6 minus 2. I get 4. 4 times 180 gives me 720 degrees. So what I know here is that all of these angles add up to 170 degrees, or 720 degrees if I add them all together. So now, if I wanted to solve for x, all I'd really have to do is just say 720 degrees equals x plus, and then just add up all these numbers. So I'm going to add up all those on my calculator, and I get an answer of 613. So all of these here add up to 613. So I'm going to add x, it has to equal 720. Subtract 613 from both sides. That means x, or this angle over here, is 107 degrees. Clearly not a regular polygon, right? Because it's not equal angular. But definitely, we can use that formula to kind of help us. So that's how we use kind of that sum of the interior angles of formula. So I like to kind of write it down as, sum interior angles. We do need to know this formula. It is n minus 2 times 180. So whatever you got to do to kind of remember this one, we're just going to kind of highlight it here so that we don't forget. All right, let's do another example. And this is kind of example 2 on our sheet, back to this sheet here. The sum of an interior angles of a convex polygon is 1800. Classify the polygon by its sides. So when we say classify the polygon by its sides, I want you to name the type of polygon. So is it a quadrilateral? Is it a pentagon? Is it a hexagon? So the sum of the interior angles is 180 degrees. So if we look back at our formula, what they're giving us is they're giving us the sum. So 1800 is what we know. What we don't know is n. And so what we're doing is we are actually solving for n here. So what I'm going to do is I'm going to go ahead and divide both sides by divide both sides by 180. And so I get 10 equals n minus 2. And then add 2, I get n to equal 12. And so what this allows me to do is then to classify the polygon by its side. If I have a 12-sided figure, that's called a dodecagon. A decagon is a 10-sided figure. A dodecagon is a 12-sided figure. So that's how you would classify a polygon, knowing what the sum of the interior angles is, and then solving for n. All right, let's go back to our externals here. I'm going to turn to page 198. We're going to talk about a couple other corollaries and theorems. This next one just says corollary to a polygon interior angles theorem. If the sum of the measures of the interior angles of a quadrilateral is 360 degrees. Again, it's kind of one of those things like just want you to know. So like whereas we all know that the triangle sum theorem tells me that all three of these, I know that the sum of those three angles adds up to 180 degrees without having to kind of do any kind of, fancy formula or anything. If I have quadrilateral, so any four-sided figure, obviously four angles on the inside, those measurements are going to add up. All four of those angles are going to add up to 360. You can think of that in a couple ways. You can think of it as, well, of course it's 360. It's two triangles, right? So 180 plus 180 is 360. But you could also use that formula, right? And you could say, well, 4. So this is 2 times 180, which is 360. So, I mean, you could kind of go back to that formula. What we're trying to get at in this corollary is this is kind of one of those ones we want you to memorize. Like the interior angles of a triangle add up to 180, the interior angles of a quadrilateral add up to 360. All right, so the next one that's kind of the big one is the polygon exterior angles theorem. So the sum of the measures of an exterior angles of a convex polygon, so again, just that word there, one angle at each vertex is 360 degrees. So imagine you had a polygon and you just kind of extended the lines out and it formed kind of this exterior angle here. And you extended this line and it formed an angle, and you extended this line and it formed an angle. So what they're saying is if you add up all of those angles on any polygon, which is kind of cool, all of those exterior angles have to equal 360 degrees. Okay? So that's going to be the formula that I want us to know. So this is the sum of the exterior angles, oops, A-N-G-L-E-S, always equals 360. There's not really a formula. It's just something that I want us to know. So again, kind of like the interior angles one, this is a little easier. We just need to know that the sum of any exterior angles, or all the exterior angles, are going to add up to 360 degrees. Go back to this sheet. So on this sheet, I gave you this polygon. So this is a 1, 2, 3, 4, 5, 6. This is a hexagon because it's six-sided. I use that above as well. So this time I extended all my sides out and made kind of those exterior angles. So what we know is the exterior angles all add up to 360. So if I took 5x and I added 62, 35, 69, 41, and 58, I added all those numbers together, which I'll do that in my calculator. I get 265. So all these angles plus this 5x has to add up to 360. So this is the algebra problem I want to see. And then what you'll do is obviously solve for x. So we're going to subtract 265 from both sides. We're going to divide by 5. And I get x to equal 19. So what x is representing is, like, if I plug 19 back in here, I could figure out what that angle would represent. Okay? So that's one way of kind of doing that type of a problem. All right, so what I'd like you guys to do now, so we've kind of, this is really kind of the gist of this section, was just really kind of a couple vocab terms and those two main theorems. So let's talk through on page 199 is kind of this extra practice stuff. I just wanted to go through, and so what I would maybe do right now in the video, because I know you guys are watching this, and obviously I can't make you do this, but my suggestion is to pause the video and try to answer this whole page, okay? So like, imagine doing this in class, and that you're gonna check your work here in a minute. So pause the video, try problems 1 through 10, and then let's come back to the video and see if you got them right. Okay, so if you're willing to do that, go ahead and pause me now. Go ahead and answer those questions 1 through 10, and then unpause me when you're done. Okay, hopefully you've unpaused me and that you've actually tried this on your own. But in case you haven't, or even if in case you did, let's go ahead and go through the answers. Okay, find the sum of the measures of the interior angles of an indicated convex polygon. So what you're going to see me do is always kind of write down the formula. Number one, it helps commit it to memory, but also just because I want to make sure that you guys understand what we're doing here. An octagon is 8. So we do need to know kind of the names of some polygons, right? So this would be 6 times 180 degrees, and so I got 1,080 80 degrees overall. A 15-gon, as far as I know, there's not I mean, there maybe is, I'm sure we could probably Google it, but a 15-gon, I don't know if there's a specific name for it, but not one that I know. So this would be 15 minus 2 times 180, so 13 times 180. Again, just the interior angles formula. I've got 2,340 degrees. A 24-gon, and I don't necessarily need you to show everything here. Like if you did this and said, okay, well, this is 22 times 180, because you recognize the formula is just n minus 2. So 24 minus 2 is 22 times by 180. I'm okay with you skipping, you don't need to write down like every tiny little step. Anyways, I got an answer of 3,960 degrees for the sum of the interior angles of a 24-gon. All right, the sum of the measures of the interior angles of a convex polygon is given. Classify the polygon by the number of sides. So this is what we kind of did on that example. So what you're going to do here is basically solving your equation. So I would set up my equation as here's the sum. It equals my formula. We're solving for n. My suggestion is to divide by 180 first. Now, I know that you were probably taught in middle school, elementary school, maybe, I don't even know, 5th grade. You would like distribute the 180. Sometimes it's not as, it's actually easier just to get rid of the 180 right from the beginning. So I'm going to divide both sides by 180, and I get 5. And then if I add 2 to both sides, I get 7. You might not know what a 7-sided figure is called, and so this one is going to be maybe a new one. It's called a heptagon. So if you didn't know that, well, write it down. Now you do. So that's a heptagon. So for number 5, I would have done the same thing. I'm going to divide both sides by 180. I get 9. I'm going to add 2. This is another one that maybe you don't know. I had to look this one up, and I don't know how to pronounce this exactly, but it's an undecagon. An undecagon. Perhaps I'm pronouncing that incorrectly, but don't hold it against me. It's a weird too. All right, so this one, 2,880 equals n minus 2 times 180. Divide both sides by 180, I get 16. Add 2, I get an 18-sided figure. Once we get kind of higher than 12, I just start naming them as like this called an 18-gon. It's not very creative, but it's a lot easier than trying to memorize all these weird names. So I would just call that an 18-gon. All right, number 7, find the value of x. So these are the interior angles. So I would do 65 plus 95 plus x plus 45 add up to, so this is a 1, 2, 3, this is a 4-sided figure. So I know that a 4-sided figure, interior angles add up to 360 degrees. So I'm going to have to set this equal to 360. I'm going to throw all my numbers together, and I get 205. And then I'm going to subtract 205 and get 155. Okay, let's see how you did on number 8. So this is a 1, 2, 3, 4, 5, 6-sided figure. So in a 6-sided figure, the sum of the interior angles, so this is would be n minus 2 times 180. Or in other words, 4 times 180. So if we grab our calculator, 4 times 180 is 720 degrees. So what I know now is that all of these angles have to add up to 720 degrees. So my equation might look like this. X plus 140 plus 130 plus 120 plus 90, even though I didn't give the number there, I put the little symbol, plus 150 equals 720. All right, I'm going to add up all those numbers. All of this stuff right here gives me 630. And if I subtract 630, I get x to equal 90. Okay, this is 1, 2, 3, 4, 5-sided figure. So the sum of the interior angles of a 5-sided figure would be 5 minus 3 is, or 5 minus 2 is 3. 3 times 180 is what? 540? So I know all these angles add up to 540 degrees. Notice that I have these two marked as the same, which means if this is x and that is x, those are congruent. So I'm going to write this as 90 plus x plus 100 plus 70 plus x equals 540. I'm going to simplify a little bit. I'm going to get 2x plus 260 equals 540. Subtract 260, and then divide by 2. I get x to equal 140 degrees. So you can kind of see how this is a two-step problem, right? I figured out the sum of the interior angles based on the number of sides first, and then I set all of these, I added up all those angles and set it equal to that number and solve for x. Watch number 10, because it's a little different, right? So we are doing exterior angles this time. And so that was kind of an easy one. We don't have to worry about, no matter what the polygon is, the exterior angles add up to 360. So I can do 4x plus 98 plus x plus 162. So this is 5x plus 260. Let's subtract 260 and then divide by 5. And I get x to equal 20. All right, so that's the lesson for today. Again, just kind of the exterior angles theorem, the interior angles theorem, kind of make sure you're able to do some of the basics. We will talk about kind of more challenging problems in class, but if you're having trouble with some of the basics, I would maybe try the big ideas lessons that are posted so that you can kind of just see if you're on the right track. And then, of course, come to class with any questions if you have any on any of this stuff. All right, bye for now.